Then it's my pleasure to introduce Carlos Augusto Bassani Varea, who will kick things off in this last plenary session today with a talk on invariant generalized complex structures on flag manifolds. Go ahead.
Thank you for the introduction, and I would like to thank the organizers for the opportunity to be here today presenting this work. This is part of my PhD thesis that I finished last year under the supervision of Luisa Martin at University of Campinas. And currently I'm in a postdoctoral fellow working with Cristian Ortiz at University of São Paulo. So the presentation today is divided in 3 parts. I will start defining the basic concepts of generalized complex geometry. So we will see what is a flag manifold, and then we are able to talk about my research with Professor Luisa Martin. And for the second talk, once we have this description of this invariant generalized complex structure on flag manifolds, we are able to talk about some geometry on it. So this is the plan for the second talk. So this notion of generalized complex structure was introduced by Hitchin and initially was developed by his students, Marco Gualtieri and Gil Cavalcanti. But nowadays it's subject of interest for a lot of researchers. And one of the advantages of this generalized geometry is that allow us to study complex and symplectic geometry in a unique framework. And this first talk is based on this joint work with Luisa Martin, which is also part of my PhD thesis. So let's start. So we are going to consider V a vector space, and denote by V star its dual. So the space where we are going to work this talk is the direct sum of the space with its dual, in this case V plus V star. And in this space, we can define this bilinear form here by this expression. Okay, and a generalized complex structure on a vector space V is defined as an endomorphism on V plus V star, satisfying 2 conditions: a complex condition that J square is -1 and a symplectic condition here. In other words, we can think a generalized complex structure as an endomorphism, as a complex structure on V plus V star, which is orthogonal with respect to this bilinear form here. Okay, so this is another way that you can think in a generalized complex structure. And the first 2 examples that appears in the literature is the examples that come from complex and symplectic geometry. So let's see. When we have J, a complex structure on the vector space V, then we can define this calligraphic J of J in this way here, which is quite simple to prove that is actually a generalized complex structure. That is, that J square is -1 and it is orthogonal with respect to the bilinear form. And in a similar way, when we have a symplectic structure on vector space V, we can define this endomorphism here, which is also a generalized complex structure. Okay, so these are the 2 first examples that appear, and they come from symplectic geometry and complex geometry. But when we are working with generalized complex structure, there is another way to look to these structures, and it's using isotropic subspace. So a subspace L is going to be isotropic when it satisfies this condition here. In other words, we can think that L is isotropic when it's a subset of its perpendicular. And an isotropic subspace will be said to be maximal when it has exactly the dimension of the space V. And the proposition that relates these 2 notions is this one. So a generalized complex structure on V is equivalent to a maximal isotropic subspace L, no longer on V plus V star, but now in its complexification, satisfying this condition here, that the intersection of L with its conjugated is 0. So this proposition relates these 2 notions of generalized complex structure with maximal isotropic subspace. So we can extend all these notions to a smooth manifold. So a generalized almost complex structure on a manifold is one of these equivalent data. So we can think this as an almost complex structure on the tangent plus the cotangent bundle, which is orthogonal with respect to that bilinear form defined in the beginning of the talk. We also can think it as a maximal isotropic subbundle on the complexification of the tangent plus the cotangent bundle, satisfying that condition that's called the real index 0. We also have a definition, a characterization in terms of the pure spinor line, but we're not going to enter in details in this definition here. It's just to know that there exists. So if you pay attention, you can see that appear this almost here in the definition when I extend the notion for manifolds. And this is because when we extend this notion for manifolds, we can ask ourselves, what about the integrability of these structures? But here to talk about integrability, we need the notion of the Courant bracket, which is defined on the smooth sections of the tangent plus the cotangent bundle by this expression here, where on the right-hand side, this first term is the Lie bracket of vector fields, and this denotes the Lie derivative. Okay, so once we have this definition of the Courant bracket, we have the definition of the notion of integrability. And a generalized almost complex structure is going to be integrable when its eigenbundle is Courant involutive. And we can think that this is a good notion of integrability because it agrees, it coincides with the notion of the simplex geometry and the complex geometry that we already know in the following sense. When we have a generalized complex structure that comes from a complex structure, then it will be integrable if and only if the complex structure is integrable in the usual sense on complex geometry. And when we have a generalized complex structure that comes from a non-degenerated tube form, it will be integrable if and only if the tube form is closed or actually is a simplex form. So this kind of recover the notion of integrability that we already have in complex and simplex geometry. So this is a real good definition of integrability for generalized complex structures. We also have another way to look at integrability in it by means of the Nijenhuis operator, which is defined by this expression here, where we have here the Courant bracket and that bilinear form that I defined before. And the proposition that allows us to use this for integrability is this one. So J will be integrable if and only if this Nijenhuis operator vanishes when we restrict it to the eigenbundle of J. And this is the equivalence of integrability. This is the notion of integrability that we are going to use in my work. Okay, so this is all we need to know about generalized geometry to understand my talk. Okay, so let's see what is a flag manifold. So we're going to consider G a semi-simple complex Lie group. It's Lie algebra, denoted by this Gottke G. We have the Cartan subalgebra of G, so we can consider the Cartan decompositions in terms of the root space. For each root alpha, we can define an element H, which is given by this expression here, where this notation here, this angle, is the Killing form. Okay, oh, sorry, and you can see the last line here because there's something in front of mine.
Yep,
okay.
I think everything's okay.
Okay, okay, and we are going to denote by HR this subspace here. So we are going to fix a Weyl basis, which is defined by this expression here. We are going to denote by pi the set of roots, and by pi plus a choice of positive roots for this Lie algebra. And by sigma, we are going to denote the simple root systems associated to this choice of positive roots. So this allows us to define a Borel subalgebra which is defined by the Cartan subalgebra plus the root space associated to the positive roots. And we will say that a subalgebra P is parabolic when it contains the Borel subalgebra. Okay, all this is because a flag manifold is the homogeneous space G over P, where G is a complex and simple Lie group, and P is the normalizer of a parabolic subalgebra. Okay, so this is the definition of a flag manifold. We have cases, but today we are going to work only with maximal flag manifolds, and this happens exactly when P is equal to B. That is, this parabolic subalgebra here is exactly Borel subalgebra. Okay, in this case, the tangent space at the origin, it coincides with the root space associated to the negative roots, which we would denote by n minus. Okay, but to do computations, it's better to use an identification using the compact real form of G, which is defined by this space here, U, where A alpha and S alpha are defined in terms of the elements of the bio basis. So we can prove that the flag manifold can be identified by U over T, where U is the Lie group associated to this Lie algebra here, and T is actually a maximal torus of U. Okay, and in this case, the tangent space at the origin is identified with the sum of U alpha, where U alpha is this space here. Okay, so this is the notion of flag manifold that we are going to work. And it's quite cool because the study of invariant complex structures on flag manifold goes back to Borel and Hirzebruch, 58, where they classified all invariant complex structure on a flag manifold. And when we have J, an invariant almost complex structure on F, then they described it in terms of the sign of the complex structure. They proved that every complex, almost complex structure on a flag manifold has this form here. So they basically are described by its sign. And the integrability conditions for these structures are given in terms of triple of roots satisfying the condition that alpha plus beta plus gamma is equal to 0. You are going to analyze triples of signs epsilon alpha, epsilon beta, and epsilon gamma, and where these three roots satisfy this condition here. And they also prove that if J is integrable, then the set of roots such that the sign is positive is actually a choice of positive roots for the system. And so this completely describes the invariant complex structures on flag manifolds. So this, based on this, we can ask, may we get a complete description of the generalized complex structures on flag manifolds, or may we get an analog of this result here for generalized structures? And the answer is yes, and yes, it's part of my work on my PhD thesis. So the first problem is to describe the invariant generalized complex structure on flag manifolds. Here I'm going to present only the case of maximal flag manifolds. But I'm saying invariant here means that it's invariant by the isotropic representation. But since flag manifolds are reductive homogeneous space, we can identify the isotropic representation with the adjoint representation. Okay. And also, by the invariance of the structure, we can reduce the problem to look only at the origin, because the structure is completely described by its value in the origin. So we are no longer looking to the whole tangent bundle plus cotangent bundle, but now we are going to look only to the tangent space at the origin plus the cotangent space at the origin. Okay. And since we have that relation between generalized complex structure and maximal isotropic subspace, let's see how this subspace, how is the behavior of these subspaces on the set that we are going to work. that is the tangent plus the cotangent space at the origin of the flag. So we have that any invariant subspace can be decomposed in terms of the roots of the Lie algebra. And we also can prove that its subspace here is isotropic, actually maximal isotropic, if and only if each of these parts that I called L alpha is maximal isotropic inside of this set here. Okay, but as I said, to make computations easier, it's better to work with the compact real form. So we are going to consider an invariant maximal isotropic subspace here, with now is the composing term of the U alpha plus the U alpha star. Okay, and this decomposition tells us that since we have this equivalence between maximal isotropic subspace and generalized complex structure, this decomposition here is telling us that an invariant generalized almost complex structure on a flag manifold can be decomposed in blocks in the diagonal, where each of these blocks is a generalized complex structure on this space U alpha plus U alpha star. Okay, so we reduce the problem of describing the generalized complex structure on a flag manifold to the problem of describe the generalized complex structure in a four-dimensional space here. So basically, we are looking for the structures, the four-dimensional structures, satisfying these three conditions here, that J square is -1, that J is orthogonal with respect to that bilinear form, and J is invariant by the isotropic representation. Okay, so after do a lot of computations, we get that there is only two types of structure that satisfy these three conditions here, and these are the two. Just to fix some terminology here. So when we have J, an invariant generalized almost complex structure on a flag manifold, we can decompose it in blocks in the diagonal, where each of these blocks is going to be of one of these two types here, which I call the first type, I call complex type, because this matrix here comes from this complex structure, this generalized complex structure comes from a complex structure. And it can, we will denote this by plus or minus J0, okay? And the second type is this one here, which we call non-complex type. And we have this extra algebraic condition here because J squared need to be -1, so we need to ask this. And it's important to note here that when A alpha is equal to 0, we have a generalized complex structure that comes from a symplectic structure. But we are going to see this with more details in the second talk, okay? So at this point, we described all generalized, invariant generalized, almost complex structure on flag manifold, because it's just you combine these two types of structure in the diagonal of the matrix. Okay, so this is the description of the almost structures, okay? Almost complex structures. So what about integrability, right? To look the integrability, we need to look the Nine-House operator and restrict it to the eigenspace of these two structures here. So we have three entries. We have a lot of combinations to do, but after do computations, we can conclude that this integrability depends on triple of roots of this type, alpha, beta, and alpha plus beta, because it's where it's going to appear that condition that Borel in Hirzebruch had of roots satisfying alpha plus beta plus gamma equal to 0. It's under these conditions that it's appeared that those conditions. And we have that a generalized complex structure will be integrable if it satisfies these conditions on this table. I mean, this table is the table of integrability conditions, where this last row, when we have three structures of non-complex type, we need to ask this extra condition here that is satisfy this algebraic system.
Carlos, 5-minute warning.
Okay, thank you. And this integrability table allows us to prove a generalization of that result from Borel and Fridrich. So when we have J an integrable invariant, integrable just to emphasize, an invariant generalized complex structure, then this set here defines a choice of positive roots. So this generalizes that result because when we have J, a generalized complex structure that comes from a complex structure, we have only this first line, and we are choosing exactly the roots where the sign of the structure is positive. So it agrees with the result from Borel and Fridrich. Okay, and we have the other case here. This lemma allows us to prove the following theorem, which describes all invariant complex structures on flag manifolds. So when we have J an invariant generalized complex structure on a flag manifold, then we can prove that there exists a simple root system, sigma, and a subset of sigma such that for J alpha is of non-complex type for all roots that is inside the generated by theta, and of non-complex type outside there. So we are basically dividing the non-complex type here and the complex type here. And reciprocally, we have that if we consider sigma a simple root system and take theta a subset of sigma, then we can construct an invariant generalized complex structure satisfying these conditions, that J alpha is of non-complex type for the roots inside the generated by theta and complex type outside there. So these two theorems describe all invariant generalized complex structures on flag manifolds. Okay, at least on maximal flag manifolds. In the case of partial flag manifolds, it's a little more complicated because the isotropic representation is a little more hard to work. But there is a study of this, description of these structures. Here's the reference of this. Okay, so thank you.
Okay, thank you very much, Carlos. Let's all give Carlos a warm round of applause. Thank you. Okay, so again, finished under your allotted time. This definitely seems to be a thing at this Junior Global Poisson. Everyone always finishes too soon. So then we don't know what to do with the rest of the minutes.
Oh, I'm sorry.
It's okay. So, okay, but Fridrich, where are you? There you are. Perhaps you can start sharing your slides. We shouldn't start sooner than half past the hour, just in case some people want to join in specifically for your talk. So I've already made you a co-host. You should be able to share. No, we can't hear you now. I don't know if that's intentional.
Yeah, let's say so. Yeah.
Terrific.
Okay. Yeah, you see my cursor, right?
Yep. Yeah, we see everything. Yeah.
Okay.
I'm just trying to calculate whether it's enough time to go make a cup of tea. Probably.
Yeah,
not.
yeah, go for it.
Well, it would be very weak. I like my tea strong.
Well, you can start making the tea now, and the next break you can.
Good idea. Yeah, good idea. That would ensure it.
So we just had a storm here, it seems.
Oh, sorry. Remind me where you are at the moment.
In Slovakia.
In Slovakia.
Oh, it's not, yeah, officially at Imperial, but
Yes, of course. But I know that you're not in London yet. Yeah. Also, I wouldn't believe you if you said there was a storm here, because I'm not that far from London, and the skies are clear, very uncharacteristically blue.
It was quite blue today, but then suddenly there was like a strong wind and storm, but now it's gone, so it's boring.
Boring.
Well, Birmingham, it's not very shiny, Nikita. So I guess.
Well, I don't know.
It may be stormy in London,
Well, I'm not in London. I'm in Sheffield, so in theory, it should be even worse. But no, it looks beautiful. Look, I can show you. Beautiful blue sky.
Oh wow! You have a good camera, also. It just focused so quickly.
Of course, I'm the Zoom master.
I can show you.
Yes. Well, you also have curtains that usually obstructs the view, kind of by definition.
Yeah.
I mean, for all we know, it's just some green screen, right?
That's true. I mean, I was just saying this yesterday, or maybe 2 days ago. I don't remember that. So many of you have met me in person, in physical reality. So I exist. But there's also many of you who have only seen me and met me through the digital realm. So, for all you know, I might be completely digitally generated. I might be just, this is just Google AI. Which is the reason why Jeffrey was speaking earlier. I mean,
is that why you pretend to have audio problems just to prove?
Did he generate you?
Well,
like his team or something?
I'm not at liberty to divulge that type of information.
So can you, if I give you a picture, can you say like where are the traffic lights and stuff?
Well, it depends on the traffic lights.
I see.
I personally constantly fail.
Oh yeah.
Yeah. So recently, I was like trying to fill. So these captchas, they're getting kind of more and more difficult. And so last time I was doing this, and I had to do it like 10 times until I got it right.
They kind of get like if you keep doing them in a short span of time, they keep getting harder and harder progressively.
Really?
I once I organized a research meeting, and I asked everyone to sign up through Zoom, and then I made a mistake and I deleted all the registrations. So then I decided, well, I don't want to bother these people registering twice, or think that I am this stupid to delete their registration. So I decided, okay, I already have all their information. I'll just register for them. So it was like 25 people that I had to register, but I had to register, each one by one. And the first time I did the capture was pretty simple. The second one was pretty simple, but then it was noticeably harder and harder. The buses became more and more distant in the images.
I think I have a somewhat mathematical question, like how big part of a car is sufficient to call it a car?
Right.
Because I'm always like wondering this corner of a car, like should I?
Yeah, precisely. That's the problem. I think I feel like sometimes I've definitely filled in the right information, but they just like it just says that no, that's not a traffic light because it's like.
Where are these rules?
Also, I'm not sure if this is true of this capture thing, but when you sign up to a website and it asks you to tick, if you're not a robot or not. I mean, obviously, it's kind of if you just think about it naively, it's very silly. But you know what it actually does, right? What it actually does is when you click on that tick box, what you do is you allow the website to access your cookies and therefore look through your recent browsing history. And so based on that, they can determine if based on browsing patterns, they can determine whether or not you're a robot.
So you can copy that from a live person.
Well, you could.
So
let's see.
Can you use this to determine whether you are a robot or not? Like on yourself?
Yes, maybe. Okay, this is a fantastic question, but we should stop. Okay, let's indeed begin. Let me introduce our next speaker, who is Fridrich Valach from Imperial College London. and he's going to talk about generalizations of Lie and Courant algebroids and its relation to exceptional generalized geometry. So take it away, Fridrich.
Thank you very much. So first, I would like to thank the organizers for putting together this wonderful conference, and then for allowing me to present the results of our work that we did together with Mark Bagden, Ondra Hulig, and Dan Woldram. So it's this paper on arXiv. And yeah, as was said, I would like to talk about a generalization of Lie and Courant algebroids and its relation to exceptional generalized geometry. And it's a long title. So let me start by a brief outline of the talk. So the talk will have, the plenary talk will have one part, and it will be about generalization of Lie and Courant algebroids and its relation to exceptional generalized geometry. And so now let's start with the algebroids. So first of all, so what are Lie and Courant algebroids? So perhaps you all or most of you know this, but still I would like to go through it and to emphasize some points that I would like to generalize later. So first of all, Lie algebroids, they are given by a vector bundle together with some additional structure. Most importantly, there is a bracket on the space of sections, and there is a vector bundle map from E to the tangent bundle of the base manifold. And this is subject to some axioms. So for example, you want that this bracket actually turns the space of sections of E into a Lie algebra. So you want that there is a Jacobi identity and there is a skew symmetry condition. And finally, this bracket is bilinear with respect to real numbers, but if you put in a function, then you cannot take it out of the slots. Namely, there is some obstruction, or not obstruction, but there is well, if you multiply the second slot, in the second slot the section B with some function, then you can take it out, but for the price of paying the extra term. So you apply the anchor map, which takes a derivative of that function. So yeah, as a result, so this is not C infinity linear, this bracket. And now what are the examples? So there is kind of of course there is many classes of examples, but the two which are particularly important are kind of trivial. So one of them is given simply by the tangent bundle, taking the anchor to be the identity and the bracket to be simply the commutator of vector fields or the Lie derivative. And the second kind of extremal example would be to take M to be a point. In that case, you get a Lie algebra because there is no row. And yeah, that's it. So that's for Lie algebroids. Now for Courant algebroids, it's slightly more complicated and also a little bit different. So you have a vector bundle, you have a bracket on the space of sections, you have the anchor map, and in addition you have an inner product, fiber-wise inner product on the vector bundle. And the axioms that you require this to satisfy are: you have the Jacobi identity, but importantly, instead of skew symmetry, you allow some non-skew symmetric part, but which is controlled in a way by the rest of the data. So if you take A and B to sections and you take AB plus BA, then you don't want this to vanish, but you want this to be given by this thing, where here we are using inner product, and then you are applying D hat, and D hat is a short notation for this composition. So first of all, you take the ordinary de Rham D or differential, turning this function into a one form, and then you use the transpose of the anchor to go in the other way. You end up with section of E star, and then you identify E star with E using the inner product. The other condition is still the same, so you have this anchor compatibility condition. And finally, a natural condition, you want that the bracket preserves the inner product. Yeah, so what are the examples? So again, one class of these extremal examples would be the ones where the manifold is a point. In that case, you get the row is not there, you still have the bracket and the inner product, and in fact, this is it. So you just have a quadratic Lie algebra. That is a Lie algebra with an invariant inner product, or invariant non-degenerate symmetric bilinear pairing. Yeah, for example, a simple Lie algebra or semi-simple would have a killing form. That's one example. Or an abelian one would also have a bracket, an inner product. The other extremal class of these examples would be the ones where you take direct sum of T and T star. So the direct sum of tangent and cotangent bundle. And the sections of that are sums of vector fields in one forms, or like pairs of vector fields in one forms. So if you take a bracket of that, then well, there is this bracket that you can take. So, and the claim is that it defines a Courant algebroid. So you see that first of all, it's not skew symmetric because this bit is not really skew symmetric. And the second point I want to make is that you can twist this meaning you can add another term here where H corresponds to a closed tree form, and you can check that if H is closed, it defines such a thing. And in fact, this class of examples can be described abstractly by saying that you have what is called an exact Courant algebroid. And this is a theorem of Pavlov-Shevera that all of these exact ones are necessarily of this form, and moreover, they are classified by the third cohomology class. Okay, so this is how the story. This is the standard story. Now the question is, or the fact is that there is another interesting object that people consider sometimes, and it's called the exceptional tangent bundle. And it's so you should see it, comparing it with these two guys, you should see it as kind of a natural next step in this. So you have this guy, then you have this class of examples, and then you have this further class. It's probably not clear why it has this particular form, but bear with me. So this is a thing that appears in the study of what is called exceptional generalized geometries. So this is physically a study of compactifications of 11-dimensional supergravity. So it's just, in a sense, it's a natural continuation. It should become cleaner soon. So for now, let's just remember that the dimension of the manifold will be at most 6. This is the case to which I will restrict. So in such a case, if you take this vector bundle, which is direct sum of Tm, the second of 2 forms and 5 forms, with this particular bracket, then this thing will have several interesting properties. So it's not a Lie algebroid because it's not skew-symmetric. It's not a Courant algebroid because it doesn't have an inner product. But it still satisfies Jacobi identity, and it still preserves something. And with something it preserves a G structure. And this G structure, what is this group G? So this group G is an exceptional, is given by this thing. So where this first factor here, the second one is kind of not that important, but the first factor is, by this I mean the split real form of the exceptional simple algebra. So you have this classification when you have this E6, E7, E8, etc. Well, I mean that's it for E's. But in this context, people usually extend that sequence to also smaller ranks just by following the Dynkin diagrams, for example. So E7 would have a Dynkin diagram that looks like this, but with an extra node. E8 would have 2 extra nodes. But as I said, we will only consider n smaller or equal to 6, so we will have just this guy. And then if you cut another node, then you get what people call E5. And that's, if you take the split real form, then you get the spin 5-5. If you cut further, you get basically this. You can stretch it to get SL5. And then you can get, if you split it even more, you get this semi-simple bit. So the point is that this is, well, yeah, okay. So let me now pose 3 questions which I wish to answer in this talk. The first one is, what is the corresponding class of algebroids corresponding to this thing? So it's not Lie, it's not Courant. It is something that people call Leibniz algebroid. That's still true, but that's not what we want. That's kind of too general. We want something really going in the direction like Lie, Courant, and something. So that's first question. The second question is, what does it give if we get M to be a point? So in other words, what does it give in this second blob of examples? And finally, the third question is whether we can use this to describe what's called Poisson-Lie U-duality. So that's a recently introduced thing by Sakatani and Malek Thompson, and perhaps some of you heard something called Poisson-Lie T-duality. So the Poisson-Lie T-duality is something older by Klimčík and Shevera, and this is somehow a new version of that in exceptional geometry. So okay, so we have these 3 questions, and so yeah, and okay, so this is what I want to discuss. So first of all, to tell you what these more general algebroids are and why they are interesting and why they are the right thing to do, because they might look a little bit arbitrary. So at the beginning, let me talk about what are the possible group setups that you can have. And you will see that for different group setups, you will recover Lie algebroids, Courant algebroids, etc. So first of all, what are the possible group setups? So they will be given by triple of data. So you have a group, you have a representation, and you have another representation, but you require this is a sub-representation of the second symmetric power of E. And corresponding to such things, you you want to have two maps which are G equivariant. You want to have such a map from E to N, and you want to have map from E to N tensor E. So if this group is semi-simple, then there is not much choice in these things. They kind of follow from this thing. But okay. But anyway, let me not go into too many details. What you should keep in mind is that you want to have this triplet of data, and associated to that, you want to have some maps which are perhaps given naturally. So yeah, and the point is that this first one, you should see this as an analog of the inner product. So if N is R, then this thing, one example would be an inner product. But yeah, so that's the idea to keep in mind. And yeah, this is subject to some number of conditions, but they are not essential, for not very enlightening anyway, so I'm not putting them here. But it's one interesting question is, what is the most general triple of such data? But since I didn't tell you what the conditions are, then it's probably not that interesting for you at the moment. But anyway, having this, you can start playing various games. So you can, for example, ask if you can define some isotropic subspaces. So for example, you can say that the subspace of E, because E is where the story will happen. That's why it's called E, the same way as E's were here and here. So you say that the subspace is isotropic if it satisfies this property. And here I should talk about this notation. So by this I mean that you take an element in V and V, and then you use this first map to map it into N. And for the reason that there will be several maps appearing, all of them stemming from this one. I mean, they will be either these maps or their duals or partial duals, etc. So to make the stuff easier to digest, we always put the well, we denote these maps by just taking a tensor product and then putting the subscript of the target. So this will be the first map, for example. Anyway, so this is isotropic. It's the usual generalization of what you might know. And if you have a Lagrangian thing, that's just a different word for being maximally isotropic. Now, somewhat differently from the usual setup, we define coisotropy. So coisotropic subspace of E is a subspace such that if you take its annihilator, so its annihilator is something that lives in the dual space, and then you project it to N star. So here we are using the second map from E star to N star, which is just a rewrite, which is just the dual of this map. So it's kind of really, in a sense, looking sort of dually to that condition. But anyway, now we can define colagrangianity to be minimally. Yeah, here one should have coisotropy. Here, okay, sorry. Here I should put coisotropy. Let me put it maybe now. No, okay, let me not put it because I don't have my tablet. Where should I? Okay, great. I see Nikita's thumbs up, so I know it's good. Okay, so this is a notion that you perhaps, I mean, people know isotropic, coisotropic, Lagrangian. So here we are forced to define also this co-Lagrangian, and it will turn out to be different than Lagrangian in some cases. So let me go into examples, because that's where the stuff gets interesting. So first of all, if you take just the general linear group GL with the vector representation and with trivial n, then, well, yeah, that's one example. You should keep that in mind, because that will correspond to Lie algebraics on the next slide. If you like pictures, then here's the linking diagram for SLN, and this is the representation corresponding to this Rn. The fun fact is that since n is 0, it means that any subspace is isotropic and coisotropic at the same time. And in particular, it means that Lagrangian, meaning maximally isotropic, the only subspace you have is the space itself, so the full E. Now, the second example, which will turn out to correspond to Courant algebraics, is given by the orthogonal group. So this is O and N, and with vector representation and with R, where you see this R in the second symmetric power of this, meaning that this thing you want to really, in this case, this thing is really the inner product. So here's a picture, and in this case, you can check that the Lagrangian and co-Lagrangian, they mean the same. They both mean that you have a half-dimensional isotropic or half-dimensional coisotropic subspace. Yeah. So, and the stuff which is interesting for us now is the exceptional case. So we have E and N times R plus. So this is the group I introduced before, and I don't tell you explicitly like here, what are the representations? I will just tell you in terms of Dinkin diagrams. So if you take, for example, this is the E5. So E will be always the node on the left and N the one on the right, more or less. So point is that this is just some specific choice of representation satisfying these conditions that I didn't tell you what they are. And the point why we are considering this is that this corresponds to some physical considerations. And in particular, there is a funny thing happening here, and that is that if you study what the Lagrangian subspaces are, then you will see that there is two classes of them. There is ones that are of dimension n and one that are of dimension n-1. And some buzzwords for that. So these ones are related to M theory, and these ones are related to string theory of type 2b. Maybe I can comment more on that in the parallel session. Take it as an advertisement. Yeah, another funny observation is that if you look at the Dinkin diagrams, and this is precisely the ADE correspondence. And perhaps another funny thing to mention at this stage would be that if you want to play some games, for example, introduce some metrics and stuff, then in this case you will recover Riemannian geometry, or which well, yeah, or if you complex structures, then okay, maybe later on that, so because I didn't introduce the algebras yet. Okay, just to finish this slide, there is an extra example that you can do. You can take SLN times R plus, so basically this one, but not take n to be 0, but instead take E and N to be second and fourth wedge. So finally, if you look at these things, then if you take only 4 nodes, then you recover precisely the example from before. So that's E4. If you take 3 nodes, then you recover precisely a special example of this one where you have only 3 nodes. So you have E sitting here. So that would be if you would just take these first 3 nodes. If you take only 2 nodes, you get the special case of the first example. So this is this gives a kind of a nice cross sections of these. Anyway, the point of this thing is that you can show again that the Lagrangians, they're of different type. There are n-1 dimensional ones, and there is 3-dimensional ones. And this is a funny exercise to do, actually. You can prove that by simple induction. And this was studied in this work. I mean, as an algebra, this is perhaps a fun thing to do, but so far it's not clear how it relates to anything useful. So let me go into that. And this is the definition of G-algebraics. So the definition goes as follows. We start with a principal G bundle. So for a given G algebra, we always assume we have picked this admissible group data set, this GEN triple. Okay. So if we have that, and if we have a principal G bundle, then you can associate with some bundles E and N, which are by a mild abuse of notation, I did not buy the same letters. So you have 2 bundles. They are associated to these representations. And then you want to have some structures on that. For example, you want to have a bracket on this E. So you should still look at this guy. This is the main protagonist. But around it, there is also hovering this N and this principal G bundle. Anyway, you want to have, sorry, the G algebroid by definition is this structure together with a bracket on the space of sections of E, an anchor map, so a vector bundle map from E to Tm, and some novelty here, some operator that should go from sections of this guy to sections of this guy. And the conditions that you want to have, again, you have the Jacobi identity, you have the anchor condition. Mimicking the current algebraic axiom, you get precisely this condition here. So this is the controlled symmetry of the bracket, if you wish. So here we are using, we take the 2 sections, take the map to N, and then you use this curly D to go back to E. And furthermore, you want some sort of analog of this condition here also for this operator D. So you also want that if you put a function here, it goes out, but there is an extra term given by this determined in terms of these structure maps. That's not too important. The important point is that it's this plus something specific. And then finally, you want that the natural condition, you want that the bracket preserves the G structure given by this G bundle. Okay, so this is perhaps, given the previous slides, maybe it's not that surprising that you have this structure emerging. Perhaps it is still surprising. So let me tell you some consequences. So one simple consequence is the one that you always want, that the anchor preserves the bracket. But that's a general truth following from this and this. more interestingly, we have that the image of D is actually left central. So if it's bracketed with anything, is 0. But most interestingly, you get, for those of you who know Courant algebra, so here you get again some sort of sequence, some chain complex, and that one is given. It looks almost the same as the one for Courant, but it's slightly different. So it looks like this. So you have E, you have Tm. This is the anchor map, and here you have T star M tensor N. And the map from this bit to this bit goes by taking the transpose. So here you get something in E star, and then you use this group thing coming from these two maps to map it to E. But morally, it's the same type of thing, kind of. And
yeah. 5-minute warning for you.
Thank you. And so now we can make the natural definition. We say that the G algebroid is exact if this sequence is exact, meaning it's exact here and here. Okay, and now we can go to the examples. So first example is the one given by the first example here, and that one, as you see, if you take n to be 0, then this condition drop. I mean, the right hand side is 0, meaning this is Q-symmetric, and the other conditions kind of drop, so you get that this is Lie algebroid, really, like. And exactness, if you look at the exactness condition, so if you take n to be 0, then you get 0 here, so exactness of this sequence means that E is Tm. So you see that this class here, the first class, was really some sort of exactly algebroids, if you phrase it in this language. And if you take the orthogonal group, the ONN, and in addition you require that this curly D is given by this, this D here. That's an extra assumption that you must make, but anyway, then this gives you precisely Courant algebroids. And moreover, this notion of exactness will reproduce the notion of exactness from Courant algebroids. Yeah. But as I said, this is just some known stuff. So the point was to apply all of this to this exceptional case. And that's my last slide for this plenary talk. So in the exceptional case, first of all, because that's the main point of our study, so it deserves a special name. So in this case, when you take G algebroid for this group data set given by the exceptional group, then we call it the exceptional algebroid, or somewhat heretically we call it an algebroid also, because that's a short for exceptional algebroid. And if you look at what the exact algebroids or exceptional algebroids are, then you will see that they again fall into two classes, depending on whether the base is n or n-1 dimensional, where n is the rank of the associated group here. So yeah, and yeah, so we call them M-exact and 2B exact. And the reason why they split again into those two classes is the fact that from the axioms you can show that kernel of this row is always should be, yeah, in this case it's Lagrangian. Yeah, the kernel is Lagrangian, and Lagrangians, they are kind of corresponding to the Lagrangians, and we saw before that Lagrangians, they are of two types. And so in the work we focus on the first class. There is an work in preparation for the second one. It should come out very soon, but this is the easiest one, the easier one. And so the theorem we proved is that, in fact, if you take any M-exact algebroid, then it is locally of the form of the exceptional tangent bundle. So that was this guy here, this complicated stuff. So all of this is local. The proof kind of reveals some ways to do the global stuff as well. So it like leads to introduces twists and everything. Okay, so let me just finish by saying what would await you in the parallel session if you would come, and that would be a discussion of Poisson-Lie duality and of some dynamical aspects of the theory. So Poisson-Lie duality is something that in the orthogonal case it reproduces the Poisson-Lie T duality, and in the exceptional case it reproduces the new Poisson-Lie U duality. And in this case it turns out to be trivial. And the dynamical aspect would include generalized metrics, connection torsions, Ricci tensors, and such like. And that is all, and thank you very much for your attention.
Okay, thank you so much, Fridrich. Let's all give Fridrich a warm round of applause. I want to take this opportunity and extend special thanks to Fridrich for stepping in at the very last minute. The reason is that we, as many of you probably know, we originally were scheduled to have Aldo Witt as our speaker, but unfortunately he had to cancel at the end of last week, and I contacted Fridrich, and we had a 5-minute negotiation, which I suggested to him if he could step in as a replacement speaker, and I said, and he told me, okay, give me 5 minutes to think about it, and I said, well, take 30, because I mean I know it's not an easy decision with only so few days to spare. And he said, okay, give me 7.5 minutes. And within 8 minutes, he had the answer, which was yes, which we're all truly grateful for. Thank you for preparing such a wonderful talk in such a short span of time. So why don't we give Fridrich another round of applause just for this heroic effort.
Okay, thank you. No, I'm very grateful for being invited by you. That's so we should also give a round of applause to Nikita.
No, thanks. That's okay. Okay. So where is our next? So we seem to be missing our next speaker, which is great news. So let's wait for a few minutes. I mean, I know it's not time yet. He still has 3.5 minutes technically. But if anyone is aware of Xiudi's whereabouts, please do let us know. Because we would desperately like to know. So we're going to wait and see if he connects. Maybe for 5 minutes past, past the hour. And if he still doesn't connect in that time, then maybe we could just take a break until half an hour past the hour for Carlos's talk. I think so I'm suggesting that we still wait instead of Carlos is starting now, because as usual with all these talks, there might be someone who might want to connect specifically for your talk, so we don't want to start early. But let's just hope Xiudi connects. I've sent him messages basically everywhere I could. Yeah. So this is an even longer pause that I have to try to fill. I've not been trained for this.
Do you want me to continue with the talk?
Well, ordinarily I would say yes. I don't know. Okay, let's just wait for a few minutes. Yeah. Maybe this is a good opportunity for me to go and make myself a cup of tea. Okay.
By the way, Nikita, I don't remember. Did you advertise our tomorrow's event with Anton Alexeyev?
So maybe. So good idea. Yeah, I think I have advertised it, but it's certainly worth advertising again. So tomorrow
not today. So yeah.
Sorry. Oh yeah, but I did not advertise it
today. Yeah. So.
Yeah. Yeah, so our program continues tomorrow, so we don't have any more junior speakers after today, but we do have more activities, and one of them is particularly exciting, which is it's called topic-based discussion session, and it'll be chaired by Anton Alexeyev, and basically we asked him to give his experience and point of view on on a specific subtopic of Poisson geometry, and we've asked him to talk about the moduli spaces, Poisson and quasi-Poisson structures on moduli spaces of homomorphic or just connections, flat connections. So he's going to formulate, hopefully, some questions, open problems in a way that is accessible to us, and something that many of us could potentially get excited about as junior, early career researchers. So it's the first time we're doing that kind of activity. It's inspired by a similar type activity that we saw at another conference, which we loved. We thought it was great, so we're trying to replicate it in some way. So we'll see how it goes, but I'm really looking forward to it. I think it's going to be excellent. And then so that should last for somewhere between 45 minutes and an hour. And then after that, we will all go, as I said, like on a little field trip to the Global Poisson webinar to listen to Nigel Hickson. Oh, Xiudi is here. Hi, Xiudi.
Hi.
Hi.
Hey.
Okay, so I am. I've just made you a co-host, so you should be able to share your slides.
Okay.
Okay, perfect.
Okay, let me introduce our next speaker. So my pleasure to introduce Xiudi Tang from University of Toronto, who will tell us about symplectic excision. Sorry.
Okay, thank you for your introduction. Yeah, today's topic is symplectic excision. So this is a work joined with Yao Cashon and was posted on arXiv. So what does it mean by the title? So there are a couple of symplectic accessibility conditions we named. Basically, you in the symplectic geometry, you're wondering, given two symplectic manifolds, when are they symplectomorphic to each other? And a big category is given as a big symplectic manifold, and you want to consider a large enough open submanifold of it. So you choose a closed subset, usually small, and you remove that subset so that you want to know that if the complement of the closed subset is it's somehow equivalent to the ambient manifold. So there are a couple of questions given a manifold and a closed subset of it. First, is there a diffeomorphism from m minus z to m? And so this is a question in smooth category, and in symplectic category, we wonder if there is a symplectomorphism from m minus z to m, or can we choose the symplectomorphism to be supported in an arbitrarily small neighborhood of the closed subset Z? And so the first one is smooth excitable. Second one is symplectically excitable. Third one is symplectically neighborhood excitable. And the fourth one, can this symplectomorphism to be realized as a Hamiltonian flow whose forward flow preserves Z. So imagine that you can find a Hamiltonian vector field which can be time dependent that pushes this subset all the way to infinity. And the last condition is can this Hamiltonian symplectomorphism to be chosen from a time independent function. So we give the names of these conditions. And you can see that actually these assumptions are more and more restrictive, right? So if we draw a diagram, so time-independent Hamiltonian excitable implies Hamiltonian excitable implies symplectically neighborhood excitable implies symplectically excitable and implies smooth excitable. And the first questions would be whether the ones on the left can imply the ones on the right, or they are equivalent to each other. So which one do you know that cannot imply the other ones? For instance, if a subset can be removed from a manifold, by the way, here if you want a meaningful question, this manifold M must be a non-compact. So there's a symplectic Campbell space. So you consider what is the symplectic Campbell space. This is a very famous example. You can consider a wall x1 equals 0, a three-dimensional wall in 4 dimensions, and you remove both. The wall has a hole. The hole is a three-dimensional ball. So you remove the three-dimensional ball from a three-dimensional wall, and this is a wall with a hole. And if you put that in R4, then the complement of the wall with the ball is diffeomorphic to R4 because you can just drag the wall. Drag the hole to make it larger and larger and all the way to infinity. So this is symplectic. So this is smoothly excitable from R4. However, if you think about a symplectic excitation, you realize that the complement of the wall with the ball, the symplectic Campbell space, is not symplectomorphic to R4 because there is a symplectic invariant, which is the size of the maximal size of balls that can go through the hole in the wall. So the isotropic space of the embedding of the symplectic embedding of balls is not connected if the radius of the ball is too large, and so the threshold of radius is a symplectic invariant here. So this is an example that a smooth excitation exists, but the symplectic excitation cannot exist. So this is our first example. The first two are not the same. So we really have a new, really have invented a new terminology, a new concept. So and there's another observation is that if you want a symplectic neighborhood excitable subset, the subset must have 0 symplectic volume. So it must be a null set. And the Z cannot contain any open subset. So usually Z must have a codimension at least 1. So in our examples, you only and this is already required by a symplectic neighborhood excitation. Here, therefore, an easy example is a half space. The half space is symplectically excitable from the entire space because if you remove it, you get another half space, and the half space is symplectomorphic to the entire space. But this is not symplectically neighborhood excitable because it doesn't have 0 symplectic volume. So the symplectic excitability is not the same as symplectic neighborhood excitability. So now we have two more questions. What about the symplectic neighborhood excitability, Hamiltonian excitability, and the time-independent Hamiltonian excitability? So are they equivalent to each other, or they are essentially different? Now let's look at some examples that we have verified. So basically, this is the first example, and this is the center. This is ignition of our interest, is the question circulated by Alan Weinstein, that if you have a properly embedded ray, if you properly embed a ray into a non-compact symplectic manifold, and you remove the ray, you can consider the complement of the ray, and is it symplectomorphic to the ambient symplectic manifold? The question is, the problem is solved in a positive way, and history of the solution is that I wrote a paper on IMRN, partially solve this question, that proves that this is symplectically excitable from. It's symplectically excitable. An array is symplectically excitable, but with some additional assumption from any non-compact symplectic manifold. And then Stratman gave a complete proof of this theorem with no assumptions. And what we have done is that we prove furtherly this is not just symplectic excitable, but it's time-independently Hamiltonian excitable. It means that we can find a time-independent Hamiltonian function, and you can use the time-one map of that function, of that Hamiltonian flow, to gradually, smoothly push that ray to infinity. So this is not the right graph. Sorry. So imagine you have not this guy. You have a ray in. So you can imagine any non-compact symplectic manifold and any proper embedding of the ray, and you can always remove it. So no matter how twisted the ray is, or how badly the symplectic manifold looks like, you can always remove it from it by a Hamiltonian, by a time-independent Hamiltonian. So this diagram is not correct. Sorry. The second example using our method is that you can remove a box with a tail. What is a box with a tail? Is a union of a box. So this is it's a box, union of a box with a ray. So this guy is not a manifold. It has some. It's a manifold with corners. I can't even say that, because it's a mixture of dimensions. So, but we can still use our theorem to remove a box with tail from R to N. Remove a shape like that. This shaded plane is a hyperplane, and the box with tail is a subset of the hyperplane. It has codimension 1. A third example will be even more complicated topologically. So you can consider the Cantor brush. So the Cantor brush is just the Cantor set multiplied by the ray. So you have a family of ray, but the family is parameterized by the Cantor set. So this definitely not a manifold. And our algorithm, we can use a smooth Hamiltonian flow to push this guy to the right all the way to infinity without exciting any other part of the manifold. So we can remove the Cantor brush. So the Cantor brush has oh, wait a minute, I guess there's a typo here. So this should be 2n minus 3. So then the Cantor brush also has the codimension 1. Oh, no, sorry. Oh, sorry. No. The Cantor brush has dimension 2. So, and the codimension is at least 2. So this is okay. And there's another example. You can, if you have a finite tree, and you properly embed it into any non-compact symplectic manifold, and you want to embed so in a way that the root is pointing to the root goes to infinity. So I mean you can say that the tree will contain all the leaves, but does not contain the root, and you embed it properly into the manifold. The root must be sent to infinity. So this is and the ray is a special case of the open-rooted tree, and our theorem says that, our result says that you can actually step by step push all the branches of the tree to infinity. And here is a illustration. So you can first push away all branches linked to leaves, so that you reduce the depth of the tree by 1, and then you make it, and you reduce other branches, and you get a ray, and the ray you can put the ray to infinity. So this way we can push any finite open-rooted tree to infinity by actually using the time-independent Hamiltonian excision multiple times. So let's take a closer look into the first and the simplest and the motivating example, removing the ray. So we say that any non-compact symplectic manifold is symplectomorphic to its complement of any properly embedded ray, and moreover, the symplectomorphism can be given by a time-independent Hamiltonian flow. So since we construct the excision by a Hamiltonian, the shortest answer is to just write down, and we constructed an explicit function, Hamiltonian function, so just to write down the Hamiltonian function. But I still want to give you some ideas of our thoughts of the proof. How do we realize the proof? So here is a diagram of what we already have so far. So you know that we have that the smooth excitable not imply the symplectically excitable, and this actually we know that this is not does not imply, but we do not know the other two. And there were some old results, some old symplectic excision constructed in the book of the gauges in 2002, and Polyjakov told us this in 2019. But that the map they constructed is purely symplectically accessible. It's not even symplectically purely symplectic excision. It's not even symplectic neighborhood excision, and my result is somehow between the symplectic excision and the symplectic neighborhood excision, and the result by Cachon and me, the newest result proved that this is the best one, time-independent Hamiltonian excision. So this is history, and the sketch of a proof. So basically, the idea is very simple, very simple. I don't know if and any of you have ever used this idea. So you have a symplectic manifold with a smooth function f. So usually when you look at the smooth Hamiltonian function on the non-compact manifold, you would try, I guess you want to try your best to prove that this Hamiltonian flow is complete. And you do not want to see any incomplete Hamiltonian flow. But this is not good, because sometimes you want to go with it. You want to go with non-complete Hamiltonian flow. And this is and what will happen if the Hamiltonian vector field XF is not complete? Well, you would have a Hamiltonian flow defined on a flow domain that is not the whole R cross M. It's an open subset of the R cross M, and you would have some backward time function. It's not always negative infinity. It's actually an upper semi-continuous function, and it has a forward time function T. Is a lowest, in general, lower semi-continuous function. And what's interesting is that you consider the subsets given by this backward and forward time functions. Yt is all the set of all the points Sf greater or equal to minus t, and so basically this is the set of all the points you can find back. Let me see. All the points you are able to go back by time t, and zt is all the points you can go forward by time t. And now the time t flow, the time t map of XF is not from M to N, no longer a symplectic morphism of M itself, but it's a symplectic morphism from M minus ZT to M minus YT. So you get symplectic morphisms of the subsets of M, open subsets. So now we have this tool. If we can find the function f whose forward flow preserves z, and the TF is greater than 1, so on M minus z, so that would, the flow time 1 map would not excise M minus z, but it would excise all the points on z, and SF is less than minus 1 everywhere on M. Then you can calculate that Y1 would be always is empty, and Z1 is that is precisely the Z you want. So the time 1 map is would be M, the symplectic morphism from M minus Z to M. It's a time independent Hamiltonian excision of Z from M. So so do we have time?
Yeah, you have maybe three more minutes.
Okay.
Since you started late, you can have 3 more minutes, perhaps.
So here is perhaps the thing you want to see the most, is we construct a explicit function, Hamiltonian function f, on the coordinates x1, y1, xn minus 1, yn minus 1, where xn, yn, the xn is from minus 1 to 1, and p is x1 to yn minus 1, and you multiply by a bump function and multiply by yn. If you have a purely only the yn term, then it would push all the in time one would push all the points with the with xn coordinates greater or equal to 0 to infinity. So you'll push half of the space into infinity. But now we have this very important coefficient. You can see that this coefficient, if p equals 0, this is equal to 1. So if p equals 0 on the space where xn, yn equals 0, this is on the plane when p equals 0, this fz would push the half of that plane to infinity. But where the p is not equal to 0, this is you will see will be something. We have lost one page, I think. So
maybe you can tell us in words what was on that page, if it's important.
Yeah, if p is greater than if p is greater than 0, you can use a comparison with the vector field you know, and then this is become complete. So eventually,
perhaps you can give us kind of a final punchline before we end, something that could take 30 seconds.
Yeah. So yeah, you can analyze this function and the Hamiltonian vector field of the function, and you will see. So let's look at some applications. So first application is it proves that any exact symplectic form would have a nowhere vanishing primitive.
So we probably don't have time for applications. So perhaps you can just tell us in 15 seconds what you're going to talk about in the parallel session.
In parallel session, we would look at some more about the proof of a theorem.
Okay. Well, thank you very much. Okay, let's give Xiudi Tang a round of applause.
Thank you.
Okay, very good. So Carlos, I've already made you a co-host. I think you should be able to share your slides now.
Right. Let me see if everything. Can you hear me well?
Yes, we can hear you very well.
Okay. Let me turn on the lights just in case.
Good idea.
Okay, let me see. So you can see this full screen now?
Yes.
Okay, excellent.
Okay, so I guess we'll just wait like 40 seconds and then we'll start.
Okay, should I probably introduce. Yeah. Okay, so it is my pleasure to introduce the last speaker of this workshop, Carlos Zapata-Carratala from University of Edinburgh, who will talk about poly-Jacobi geometry, serendipitous discovery. Carlos, please.
Right. Thank you very much. So yes, first of all, I'd like to thank the organizers. I think you really upped the bar for the standard of a mathematicians gathering. I think it's just fantastic to see this level of production and in general the love you put into every detail, because I notice and it's great. So thanks very much for this. I'm very pleased to have the honor to actually close the workshop. So hopefully I'll be able to communicate more narratively what I wanted to discuss. We can leave the technical details for the parallel discussions, again, to the point of the good design of this event. And so, yes, so poly-Jacobi geometry. So I wanted to entice you with a sort of odd-looking title, but really I could have titled my presentation Understanding the Jacobi category. So perhaps many of you know Jacobi structures. I know many in the audience actually were the ones who introduced me to Jacobi geometry in the first place. So I want to give you my outlook on this, and hopefully I'll try to make it clear that with some clever decisions in the way we can make good progress and have pretty deep, nice understanding. But before we start, let me just plant in your minds a nagging question. Let's go back to kindergarten when you were learning about science for the first time, and when you were told you should never add together physical quantities of different kind, but you can multiply together any two physical quantities of the same kind. So we have this sort of pattern. This is kind of confusing from a mathematician's point of view. It's like, oh, why should I only add together similar kinds, but multiply together freely? And then maybe when you go to maybe primary school, you're told that physical observables are functions. And then maybe in high school, you're told that they are Jordan algebras or C-star algebras or something like that. So you have this extra input mathematically where you're told, no, actually, you can just add and multiply freely because these are algebras. And it's in definition that you can just do it freely. So what the hell's going on here, right? Anyway, I just want to plant that nagging question in your mind, and then let's move on with the talk. So this is a Poisson geometry event, so I should probably say something about Poisson. So this is the way I understand the Poisson category. I summarized it in these four terms: submanifolds, morphisms, products, and quotients. And it's an interplay between the geometry and the algebra of the two sides. So we all know the Poisson manifold is a smooth manifold that can be characterized with this bivector field that gives a musical map. And it characterizes a Lie bracket given by that formula, as we all know. And then, so we get all these elements of submanifolds first, for example, coisotropic, that we characterize as their vanishing ideals being coisotropes on the algebraic side, morphisms that we characterize as the pullbacks being morphisms of Poisson algebras, and then we also characterize as coisotropic submanifolds of the product manifold, product Poisson, which in turn can be canonically defined again with the Cartesian product and characterizing algebraically. As you all know, I'm glossing over these details because I'm sure everyone knows. I just want to paint the picture finally with a quotient there. As everyone knows, this is more or less what is familiar to, I hope, most of us in Poisson geometry. So when I went to IMPA in Rio de Janeiro a few years ago, I met Jonas Snitzer, who I think is around in this conference as well. And he introduced me to the crazy world of Jacobi geometry. And I actually learned from Alfonso Tortorella and Luca Vitagliano all this language that I'll introduce in a second. But when you first get introduced as a student, when I first got introduced to Jacobi geometry, I was a bit baffled because I knew about Poisson, I knew what I just described. I knew that we could go non-degenerate and then be symplectic. And so we have some kind of tensor with an integrability condition. We can go into the exact direction where your tensor actually is given by a total derivative. And you can make this locally conformal. You can just relax the globality and just have this kind of structures in patches around your manifold. Now, traditionally in the literature, we find the Jacobi manifold structure, what I call to be what I call a Lich-Norovich manifold structure, just to distinguish from the general Jacobi that I'll discuss in a second. And this is a manifold with a bivector field and a vector field that together can define a Lie bracket that will satisfy a Jacobi identity given some integrability conditions. And of course, if you set R to be 0, this recovers Poisson. And so again, you can go into the non-degenerate direction to find contact. You can go into the exact direction to have exact contact given by specifically a one form. And again, these objects satisfying some integrability conditions. And of course, you can do things locally conformally, and so you can have a patchwork of these sort of structures all over your manifold. So the first time you learn about this, at least the first time I learned about this, I thought, okay, so I'm very familiar with Poisson, right? We all know and love our Poisson fish, and but I thought this feels a little bit like a scary shark that is coming to eat me, and so. That's how I felt, that Jacobi had all this, there was all this literature on Jacobi geometry actually from the very beginning with Lichinarovich in the 70s, but like through the 80s and 90s with many results that resembled a lot the results in Poisson geometry, but I couldn't get one reference or one set of references that basically put a nice lace over it and said, this is Jacobi geometry, this is the end of the story. So my claim here is that the category of smooth manifolds that hosts quite successfully Poisson manifolds, in fact, might be too restrictive for the category of Jacobi structures. And so this is basically the goal of my talk today. I want to convince you that by finding the right category, Jacobi geometry becomes just like Poisson geometry. In fact, it's in some sense the same thing. So anyway, so I want to illustrate with this meme that is going to be a running theme for my talk, that the Jacobi shark is coming to eat us. And if we are equipped with smooth manifolds, if you have your Steven Spielberg trivia on point, you would remember that the quote here in the movie is, "You're going to need a bigger boat." So in our case, it's going to be, you're going to need a bigger category. So anyway, let's start with that bigger category that we need to introduce. So these are line bundles, and this is the stuff that I learned from Jonas and from Alfonso and Luca. So we are going to define the category of line bundles. These are your conventional one-dimensional vector bundles, real geometry. I do real geometry as a real geometer. Morphisms, sadly, are fiber-wise invertible. So these are general vector bundle morphisms covering general smooth maps that are fiber-wise invertible, the so-called regular morphisms. And of course, we the same pattern that we discussed, submanifolds, products, quotients, etc., can be replicated here. So any submanifold has a restriction line bundle automatically. There is a canonical construction of a categorical product that is the Cartesian product analog, which is a little bit subtle, and we're not going to details here, but you can construct such thing. And then you have the algebraic side of things, which now instead of having functions, we have sections of the line bundle. So now instead of having a functor, the C-infinity functor that sends us from manifolds to commutative algebras, we have a functor that sends us from line bundles to C-infinity modules, right? And this is functorial precisely because we can construct the B star, so the pullback construction, which allows us to send sections to sections, crucially using the fact that our morphisms are fiber-wise invertible. Now, of course, we can regard submanifolds as vanishing submodules, and there's a notion of quotient there, similarly to functions. And again, the products involve all these inclusions of the factor algebras, or sorry, the factor modules, and so on. Here, the black dots denote module structure. So again, without going into too much detail, you can see that the category of line bundles very much resembles the category of smooth manifolds. But if you do some work, and crucially, Jonas and Luca were very helpful with showing me what kind of constructions were needed for this. But crucially, there's no unit to be chosen in this manifold. So the reason why I call line bundles unit-free manifolds is because I want to think of them as a generalization of a smooth manifold where there's no canonical choice of a global unit. So this is either because you're a topologist and you're interested in abstractions for this happening, or simply because you are more of a categorical minded person and you don't want non-canonical choices, and you just say, well, I don't want to choose a unit. There might be one, certainly locally there will always be units, but there's not fixed one particular choice from the get-go. Okay, so this category is a good candidate to host Jacobi structures, it seems, and so, or at least so I was told by Jonas and company. And so let's see how the same sort of landscape of constructions, so some manifolds, morphisms, products, and quotients fit with this line bundle category. So of course, the Jacobi manifold is a line bundle endowed with a Lie algebra structure on the sections that acts as a first order differential operator on each of the entries. So in turn, we can interpret that as a by derivation in this case, by differential operator that induces a musical map from the line bundle analog of the cotangent bundle, which is the jet bundle, and into the line bundle analog of the tangent bundle, which is the derivation bundle. And of course, the same sort of formula appears for the Jacobi bracket. Again, it's entirely analogous to the Poisson case. And indeed, we can follow through with all our constructions. For example, if we have a submanifold, we can characterize it algebraically with its vanishing submodule, and this can indeed be characterized to be coisotropic when this is a Lie subalgebra of the Jacobi algebra. Similarly, for morphisms, if this is a regular line bundle morphism, we can regard that, in fact, the construction of the line bundle product is so that morphisms have a natural inclusion as a submanifold of the product. Again, the construction is a little bit subtle, but there's a canonical way to do this. And then this product allows us to just replicate the construction of the product Poisson in the ordinary case, but now with Jacobis. In some categorical sense, we're doing exactly the same thing. There's no difference here. Same formulas just now for the algebras on the modules instead of the algebras on the infinity rings of functions. And then, of course, there's also a notion of coisotropic reduction, and we have similar things. So as a summary, we can say that the line bundle manifold, the line bundle category of unit-free manifolds hosts Jacobi structures successfully, at least geometrically. But what about the algebra? So before I discuss the algebra of Jacobi, let me just briefly remind you of Poisson products. I'm sure that everyone knows about this, but I think it's good to refresh it. So remember that algebraically, Poisson is simply a pair of a commutative algebra and a Lie algebra that interact via the Leibniz identity. And if we have two Poisson algebras, A1 and A2, we can take their tensor, and we find a canonical construction of a tensor Poisson structure on this construction by taking indeed the tensor of the commutative algebras, and then given this particular definition of the Poisson bracket. So this is a standard construction on the algebraic side of things. So how does this connect to the geometry? So it is quite easy to check that if you have two Poisson manifolds, you can include these products of sort of constant functions on each of the factors into the product. And then using the product Poisson on P1 times P2, you get this expression just by direct computation. I mean, it's just an application of the fact that the cross brackets will vanish, right? And so indeed, we have a natural inclusion of the tensor products of the algebras into the algebra of the product. So that's how the algebra and the geometry communicate at this level. And we can summarize this very nice fact quite neatly in the statement that the C-infinity functor, which usually takes manifolds into their commutative algebras of smooth functions, now sends Poisson manifolds into Poisson algebras. Now, again, when I say functor and I say morphisms, this community knows that there's always a little asterisk there telling you that composition might be ill-defined and so on. But morally speaking, you know what I'm trying to say. So what about the algebraic counterpart of Jacobi manifolds? We've seen that indeed line bundles are a good host for the geometric leg of Jacobi structures. But what about the algebraic leg of Jacobi structures? So the first thing to notice is that we are lacking something like an explicit commutative algebra structure, right? So there is no commutative product on the module of sections. Now you might say, well, of course, because you've turned your ring of functions now into a module, and so the commutative product now appears as a module structure. Okay, fair enough, but still, I don't see an explicit interaction of the module structure with the Lie structure, at least not. I mean, unless you get into the deep theory of differential operators and you start building some theory, which is what we're trying to do here in a sort of tangential direction to that. Now, more importantly, is if I give you two Jacobi structures, I told you that geometrically you can easily define a Jacobi product geometrically with a line bundle product. And the question is there a natural way to include products of Jacobi sections into this product of Jacobi manifolds? Well, the immediate obvious choice doesn't work just by purely linear algebraic reasons. I mean, you're taking some tensor power of some pullback bundles, and that's nowhere near the definition of the line bundle product. So that doesn't work just prima facie, right? And now, more generally, and this is sort of the guiding question that I wanted to answer by the end of my PhD. This was my main motivation to push forward this kind of formalism, is what is the C-infinity functor analog in the context of Jacobi structures? So for the case of Poisson, the C-infinity functor sends Poisson manifolds into Poisson algebras. What is the analog for Jacobi, right? So okay, so we've seen that the geometry worked out with line bundles, but the Jacobi shark came to eat us. It ate smooth manifolds, and unit free manifolds are still desperate because they say, well, we did great for the geometry, but we broke down for the algebra. So you're still going to need a bigger category after this. So let me introduce that last category that I want to build. And let me get my time because my phone. Okay, so I think we're doing fine with time. So what is this category that I want to construct? Well, this is what I call dimension sets. Basically, A is a set, and D is a set of labels, and alpha is a surjection from A to D. So you can think of this very, very mundanely as simply a bundle in the most primitive sense. It's just a surjection of sets, nothing else. And of course, we want to take morphisms of these objects to be these commutative diagrams, as you should do. And most importantly, what we want to do is to start throwing binary operations into these kind of objects. So basically, what we want to do is to develop the traditional theory of algebra, but starting with these kind of sets that are labeled, that have types or kinds. And perhaps the nagging question I planted in your mind at the beginning of the talk is coming back to your head, because this is kind of the direction that we're going. So we want to define some operation, so some binary operations that are compatible with this typing structure, this sort of fibration, if you like, or primary, the kind of labeling that the surjection gives you. And so by a sub-index notation like this, we denote a binary operation that is only defined on the images of the surjection, right? And so morphisms of those are maps from the total sets A and B that restrict to morphisms of the maps. So indeed, we're going to see that if we introduce a second operation, so by the way, this operation is partially defined, as it should be clear. This is only defined for the pre-images. Now, if we introduce a second binary operation, now I denote by rho the projection, and this is a total operation. We can just impose the ring axioms. Again, we're trying to develop here traditional theory of commutative algebra, if you want. So axiom 1, just associativity. Axiom 2, existence of an identity. And axiom 4 is distributivity. But you might say, well, distributivity involves addition, and addition is only partially defined. How can I make sense of that axiom? So if I employ this auxiliary notation where I have subindices to indicate where the projections are, so the subindex indicates the element of G that is the image under rho, then you would see that if you demand that G actually carries a monoid structure, which is essentially the projection of the monoid structure from the ring, from the total set R, then it is feasible to demand condition 4, right? So otherwise, you would have to say this condition holds whenever it makes sense or whenever it is defined, which will be fine. But we want to be a lot more explicit about our conditions and say, well, actually, you can consistently demand this property without any extra requirement than just the literal algebraic statement, okay? So the category of these things is what I call the dimensioned ring category. And it is indeed a strict generalization of the traditional category of rings. And you can perform all the constructions that are familiar. You can define modules, you can define algebras, you can do basically all the mathematical theory that you're familiar with. And it's surprisingly, almost astonishingly natural how easily things follow with this business. And they are strict generalizations of the usual objects, in the sense that if you make G to be a singleton, so your label is a single object, then everything reduces to the conventional theory of rings, modules, algebras, etc. So indeed, this is the answer to the nagging question at the start. This is a structure that reflects explicitly the structure of physical quantities and how we think of dimensional analysis, and how you can add some things together, but not others, but you can multiply all elements with each other. So that is one partial solution to this nagging question. Back to the talk. So what was the serendipity in my discovery? So what was the connection with Jacobi geometry of this thing? So the idea is that if you take a line bundle and you take all the tensor powers, where positive means tensor power and negative means tensor power of the dual, this object naturally carries a dimension abelian group structure, if you like. So obviously each of the powers is a vector space, and you have an addition defined there. So if you just take the disjoint union, instead of the intuitive direct sum that most mathematicians will take, you take the disjoint union of this and you keep your addition partially defined, just for categorical reasons at this point. But then further, you define the following product, which is basically the conventional tensor product on one-dimensional vector spaces in the following sense. So you extend it to scalars and you extend it to dual elements and so on. You get precisely a dimensioned ring structure here. And so what's crucial here to distinguish from the ordinary ring or the tensor algebra of a manifold or a vector bundle is to note that there are as many zeros as we have dimensions. So there are set many zeros, and the tensor product actually uses the dual pairing between vectors and covectors. That's the main difference with the tensor algebra, the usual tensor algebra of a vector bundle. And so most importantly, when we apply this to line bundles, this can be done for vector spaces or vector bundles indistinctly. When we apply it to line bundles, this precisely gives us the C-infinity functor analog for the category of line bundles. So this gives a way to systematically assign an algebraic object to one of our unit-free manifolds. Okay, so that's how we made the connection. So I should be doing like 4 minutes left or something like that, just to double check with everyone.
That's correct.
Okay, great. So we come to the conclusion basically by looking at dimension Poisson algebras. So just to make a long story short, what is a dimension Poisson algebra? Well, it's exactly what you expect, but now everything has dimensions. So a set has a set of dimensions or labels, and then a commutative product has a dimension, and a bracket has a dimension. Again, this dimension, they are a bit like the order or the shifting for people familiar with the shifted business. But the axioms are exactly like you expect. There's no caveats here. That's quite surprising to me as well at this point, that you can't just define dimension commutative algebras, dimension Lie algebras, just like you do with ordinary ones, but you just need to require that your monoid structure in G is commutative and associative. Well, I mean, associative because it's a monoid already, but it must be commutative. And then if you have those two things, it is automatic that you can demand the Leibniz identity without any further requirements, even though addition is partially defined. This is crucial. Addition is partially defined. However, Leibniz identity can be demanded in that full generality in the expression. So this is just a quick check on how that works out. So the dimensions of those three elements, you can see, are those 5 letters that are just shuffled. And because this is a commutative associative monoid, they are the same, so they are comparable. And so you can consistently demand the Leibniz identity. Anyway, so what is the upshot of all this? The upshot is this theorem that we don't need to read in detail from my thesis, where I identify a dimension Poisson algebra canonically associated to a Jacobi manifold. And this is indeed the standard construction that a lot of people have done in other ways or in other versions of Poisson to assign a Poisson algebra to a Jacobi manifold. But I just did it in the dimensioned sort of flavor in my case. so crucially, this allows us to see, for example, tensor products of line bundles, of sections of line bundles as sections of the algebraic correlate of the Jacobi product. So now instead of just the sections of the Jacobi product, you have to go to this construction with the tensor powers of the line bundle. And so finally, and this is sort of the final answer to the original question, we found a functor that successfully sends, again, with the same caveats as usual functors in the symplectic and Poisson categories, that successfully sends Jacobi manifolds into well-defined algebraic objects. So if you remember that the Jacobi shark was coming to eat us, if you remember how the Jaws movie goes, I'll show you how the dramatic end of this narrative goes.
You son of a bitch.
All right, so let me just in 30 seconds tell you what the Polyjakov structures are, so that gave title to my talk, and then I'll finish here. So Polyjakov structures are basically if you give me a Jacobi manifold, I'll give you this dimension ring. And you'll have a dimension commutative algebra structure by this tensor dot product, and then you will have a dimension Lie algebra structure that has dimension exactly -1. And so the immediate thing to think is, well, what if I just change that to be any integer? And most interestingly, you can reproduce this construction for a collection of line bundles over the same manifold. It's just a trivial construction, and so you can further consider the same kind of thing with that bracket. So these brackets are interesting because they don't recover any particular Jacobi bracket. They don't correspond to a Jacobi bracket anywhere in particular in general, but in a categorical sense, they are exactly identical to Jacobi brackets. So this is what I call the Poly-Jacobi brackets. And just to summarize here what the outlook is for the parallel session, I'll just say that it'll be interesting to extend Poisson geometry results to the dimension category, see traditional techniques applied to these sort of objects. For people in the audience who I know are very knowledgeable of the shifted Poisson business, I think it'll be very interesting to see what the translation is between these two, because I think it might be very direct. Of course, applications to geometric mechanics, because I mean, after all, we're talking about something that is compatible with this idea of physical quantities being having that structure of dimensional analysis. And then finally, I just think that this is another instance of a Poissonization trick, where you take some object, you do something to it, you contort it, and then it turns out to be Poisson again. And so I'll just leave with this meme that summarizes that Poissonization culture that is very common here. Thanks very much.
Okay, thank you very much, Carlos. Let's all give Carlos a warm round of applause. So thanks a lot. Yeah, so thank you. Oh, I can hear myself. Okay, great. No, I don't. I think it was not from you, Carlos. Yeah. So okay, wonderful. Thank you. So this was our final junior presentation talk. We now move on to the parallel session, final parallel session. Don't forget that the program continues tomorrow with a topic-based discussion session, the Poisson webinar, and then the Thursday social, which will also at the beginning there will be the award ceremony for the awards for best contribution, which I can totally see will be very difficult for us to judge. Very, very difficult. So, okay. So I encourage everyone to take maybe between 5 and 10 minutes screen-free break. Maybe make yourself a cup of tea or coffee. So the parallel sessions, I'll open the rooms in a few seconds. Parallel sessions, I expect them to begin roughly 5 minutes past the hour. Okay.